This is part 2 of the chemical bonds review, and this will be questions 31 through 49. And let's see, we're beginning right over here at question 31. So, what is the chemical formula when calcium bonds with oxygen? Let me zoom in here a little bit more. So what you have to be able to do on this test is that you have to be able to look at the periodic table. Well, we got the element list first off. We got calcium, Ca, which is located right here. It is in group 2 of the periodic table, so it'll have a Lewis structure that looks like this, which means it's going to lose 2 electrons, making, when it loses those 2 electrons, it'll have a 2+ charge, oxidation number. So we'll do calcium 2+, that's its oxidation number. And you'd figure that out by drawing its Lewis structure and see if it's going to be easier to gain or lose electrons, and then count how many it gains or loses. Oxygen, over here, is in group 16. When you draw its Lewis structure, you end up with something like this. Oxygen needs to gain 2 electrons to become stable. When it does that, it'll have a -2 oxidation number. So that's how you're going to have to figure out these oxidation numbers, which is just another name for the ionic charge when they either gain or lose electrons. So we're going to bond it together with oxygen with a -2 charge. Let's see, so I'm going to do this on the back just because I didn't leave you much room. So this is where you do, let me see, what's the chemical formula? All right, so we're going to do calcium plus 2. This is what we learned in class, the crisscross method. So you start with the 2 elements, what their ionic charges are. We do the crisscross. We take the absolute value of that, and that becomes calcium 2, oxygen 2. But one of the rules for doing crisscross method to figure out how many of each element, if we can divide these by the same number and reduce them, we do that. So this becomes just calcium oxide, like that. Is this ionic or covalent? Well, ionic bonds are metals and nonmetals bonding. And this is a metal, and this is bonding to a nonmetal. This will be an ionic bond. As we'll talk about here in a moment, you could also take a look on this chart of electronegativities. And let's see, oxygen's electronegativity is 3.5. We subtract calcium's electronegativity of 1, we get 2.5. And if we get a number when we subtract those greater than 2, they're ionic. So one way you can tell they're ionic is subtract their electronegativities, but if it's a metal and a nonmetal, it's going to be ionic. Number 32, list the characteristics of covalent, ionic, and metallic. We want you to include melting points, conductivity, malleability, and brittleness. Well, I'm just going to turn this into a data table. And the first thing is, okay, with covalent bonds, I'm just going to put shares, pairs, that means 2, pairs of electrons. Ionic bonds, give or take electrons. Metals give electrons, nonmetals take. They give or take electrons. Metallic, they share electrons singly. Oops, I misspelled that. With any atom. They're not just teamed up with one, with any atom. In my class, we did the throwing the valence electrons all over the room to signify that they're sharing it with any atom, not just back and forth. A covalent bond, if you have a hydrogen, they're going to be sharing their electron back and forth, each one between them, the same one. Where the metallic bonds, they're going to be sharing one electron all over the place. So let's see now, melting points. Let me do melting point. So covalent bonds, very low. In my class, I had you put sugar under the Bunsen burner and it melted almost immediately, low melting points. These are very low energy bonds. It doesn't take much energy to break a covalent bond. In fact, covalent molecules very often can be existing as a solid, like sugar. They can exist as a liquid, like alcohols and things like that, or they can be gaseous, like the air we breathe is a mixture of oxygen and nitrogen gas, which is a covalent bond. So they have very low bond energies. It's real easy to break them apart, and because of that, they can exist very easily at room temperature as any one of these. I think there's a test question on that. You might want to really pay attention to that. Now that was for covalent. Ionic molecules, a melting point very high. Okay, it takes a lot of energy to make that electrostatic. Let me do a sodium ion electrostatically, that's what that's going to be, connected to a chlorine ion. This I'm just going to abbreviate it ES. This electrostatic attraction is very strong. It takes a lot of energy to break it. This is the strongest of the bonds right here. Ionic bonds have the highest bond energy. It takes a lot of energy to break them, and that's why when you're in class, it took a long time for that piece of salt to melt. And then metallic. Now, because they can quickly share their electrons, their melting point, they have high melting points as well. Okay, so let's see. Let's go on over here. We've done melting point. Conductivity. In our lab, we found that covalent compounds had low or really no electrical conductivity. They cannot conduct electricity. Now, when I mixed up our stuff in class, I inadvertently mixed it with tap water, which had some salts in it, so that's why we got some conductivity. But pure covalent compounds like the alcohol, it had absolutely no conductivity. Ionic compounds, they can conduct when melted or dissolved in water. Dissolved in water. Metallic conductivity, very high. Because they are throwing those electrons all over the place, you can add electricity to it, and it just carries with it very high conductivity. Our next one, malleability. Whoops. Well, I'm just going to go malleability. Now, that's the ability to be hammered into shapes. Hammered into shapes. And so covalent molecules, no, they can't. They're kind of soft, and they're like powders. Think of sugar. I mean, they're brittle if they're a solid. Ionic compounds like salt, they're brittle. They are not malleable. You just imagine hitting a salt crystal, it'll shatter. See over there. Now, with metallic elements, very, very malleable. They can be hit and pounded with irons and forges, so metals are very malleable. And actually, I did malleability and brittleness as well. And let's see now. So the last thing over here, I wanted to mention here the characteristics. We said that covalent compounds, they share pairs of electrons. They give or take electrons for ionic. They share electrons single with another atom. The other definition for those is also at the end over here for covalent, non-metals bonding. For ionic, it's non-metal bonding to a metal, so non-metal to metal. And for a metallic, it's metal to metal. What is a crystal lattice? Now, in my class, we started building those little crystals. If you get, in class, we were doing sodium chloride. We had a big negative anion and a little positive cation. Well, what happens is, this is what they call a unit cell, a unit formula for salt, NaCl. It's a sodium ion and a chlorine ion. Well, when they start to attract, they can attract another salt compound there, like this. Then you can get another big one and a little one. And this repeating pattern is the structure of alternating anions with cations. That is a lattice structure. Lattice means a structure. Why does this form? Because these pluses are attracted to minuses. So the crystal lattice will form. because we got electrostatic. Let me put that down here. It's due to electrostatic forces. And again, that means you've got plus charges and minus charges that are being drawn towards each other. What type of bond forms this structure? Ionic. Excuse me. What holds the atoms together to make this shape? Well, it's going to be the shared electrostatic forces attracting in, because what happens is when you build this up, eventually you get enough of these, you start getting it. In class we were getting the beginnings of making a very large square crystal of salt, but it was made from these repeating little patterns of large and small, large and small, large and small, that just repeat over and over. And it's the electrostatic forces, the intermolecular forces. For ionic, it's the strongest ones, which are called electrostatic. Number 34. Did I get this number? Yeah, 34. Why do water molecules stick together? Well, we're kind of getting into what, polar and nonpolar compounds. And a water molecule, when we draw it, now water is going to have its two pair. When we did the Lewis structure for water, it's got two paired electrons. It's going to have two unpaired electrons, which it will share. I'll do those in a different color for hydrogen. It'll share those guys like that. So what happens is you get this water molecule. Let me clean this up now. Looking like this. Water's more electronegative. It's got a really high oxygen, is more electronegative. So this side is going to be partially negative because electrons are spending more of their time here. And this side will be partially positive because their electrons are being shared unequally over there. And the symbol we do for that, you can say this is the plus side, if you like, of the molecule, and the arrow points towards the negative side. So this is a polar molecule because it's polar, because it does have a partial plus side and it has a partial negative side. And so why do they stick together? Well, what happens is that this partial negative oxygen can attract from another water molecule, which I will do in green here. So if we got another water molecule over here, it's going to, the partial positive of this hydrogen is attracted to that partial negative, and they form a very weak link. And that weak link that I'm drawing as dotted lines is called a hydrogen bond. So a hydrogen bond, now I'm going to just redraw a water molecule like this, just trying to make it neater. Here's the water molecule. I'm going to draw another water molecule here. I'm going to put the oxygen end here. The hydrogen's coming off. So this end, 3 dots. This is the partial negative end. This is the partial positive. This hydrogen bond is a weak attraction between polar molecules. Polar again means it has a plus and a partial plus and a partial negative side between polar molecules. Polar molecules happen because in covalent compounds they do share electrons, but sometimes one of them shares it more. When hydrogen, okay, now we're going to be looking on this chart, hydrogen over here, forms a bond with a halogen, what type of covalent bond is formed? Now at first, okay, it's going to be a covalent bond because hydrogen is a nonmetal, even though we put it in the alkali metals. But when we subtract, here's the halogens over here, fluorine, chlorine, bromine, and iodine. So let's get hydrogen has an electronegativity of 2.1. Now, water is, hydrogen is 2.1. We're not doing water, we're doing the halogens over here, sorry. So let's just have it bond with fluorine. So if this is hydrogen, if this is fluorine, fluorine's electronegativity is 4. That's the highest attractiveness for an atom. When you do 4 minus 2.1, we'll use this chart down here to see what number range it comes into. Now, by the way, this is the chart that you'll have on the test. Okay, that's going to be your reference chart, as well as I'll give you a periodic table.